So this presentation is basic hydraulics, and there may be a couple of hiccups here. This is basically my bring everybody up to speed presentation that I would do in person at the Academy. And I'm doing it as more of an S211 refresher to kind of get everybody on the same page and speed that process up. Uh, with that, this run of it won't necessarily have the student workbook, so there's a little bit of material that's missing, and I may glance over a few things, but it should still give us the basics of how to do these hydraulics calculations and why. But just because we're doing that S211 refresher type of approach here doesn't mean we shouldn't delve into the specifics of why, when, what we're really trying to get to here. So why do we do hydraulics? Why do we look at this hydraulics calculation? And the easiest, simplest answer is to get that pump discharge pressure. I do all this basic math and it gives me a number, and that number tells me what pressure I need to be able to pump my hose lay, and that's the simplest form of it. But really the next step, and just as critical, is to determine the appropriate equipment to be able to do the job. Not all equipment can produce the needed pressures and volumes, so that's why we start looking at hydraulics, is troubleshooting why a system won't work, or better yet, troubleshoot the system before we ever try to pump the system. And then the next piece is you can pump anything. It's all pumpable. Whether or not the levels of commitment you have to go to make a hose lay work are worth it is something to be debated on the fire. But it can be pumped. It may not be worth it, but it can be done. And by having a solid understanding of hydraulics and how all of these factors play together, that gives you the opportunity to figure out how to make it work. So objectives, really we're going to cover this in more of a classroom type environment, and that'll be, it will delve into this a little bit more, but determining your pump discharge pressure is the underlying initial objective, and probably the primary factor of where we're going to get to initially today. But there's no way that's true, because there's no way I can determine pump discharge pressure without using that to determine the pump performance needs. So we'll tie those two together, and then depending on how this all goes, we'll look at functions and complex hose lays and how we can make all that stuff actually come together and work. How to pump it. So considerations, these are the things you need to know to be able to run your hydraulics equation. You need to be able to answer these independently and then plug them into that to give you the numbers that you're looking for. And then what you do with those numbers is the next step. But to start with, you need to know what nozzle pressure you are going to use. That you need to identify that ahead of time. Ultimately, in this equation, you're basically solving for nozzle pressure. The end result of the whole game is to get that 50 or 100 psi to the nozzle. The rest of it is how you get that portion of the equation solved. Albeit pump discharge pressure tends to be the answer. Ultimately, you need that pump discharge pressure to produce your desired nozzle pressure. So you're going to need to know what that is. You're going to need to know your head or head pressure. That's your elevation and the pressure loss or gain based on going up or downhill. You're going to need to know the volume you are flowing out each nozzle and therefore out your pump. And you're going to need to know friction loss. And that's a function of that volume and your hose diameter and length. Okay, so how to read or write a hydraulics problem. This is getting us all on the same page. Common terminology, common operating picture. So we're kind of stepping away from the cool graphics and getting it down to the simplicity of form of what we actually do. This is how it would look if I write it on a piece of paper, if I write it on the hood of my truck. And this is the format I draw it so that I can work it out that way. There we go, right on the side of a fire engine. You know, it's a little rougher, it's a little less specific, but ultimately that's kind of what we're doing. We're just got to all get on the same page so that we can all read these problems and be talking the same way. So I'm looking here, identifying parts. The pump. The pump's going to be this circle over here. Okay, it's sort of self-explanatory, but maybe not. It's possible that some people aren't necessarily knowing that. And depending on the picture that you run into, that may be a square. That may be, you know, a bracket with some, you know, pump models assigned to it. It might be a circle with the pump models written in it. They can vary, but something's got to depict where my pump is. Sometimes it's a square with an X in the middle. The hose lay is the lines identified by length and size. So as I go up from my pump, I'm looking at 500 feet of 1.5 inches. All right, there's 500 feet of 1.5 inches hose that goes from my pump to my first Y. All right, and then I have a lateral that's 100 feet of inch that comes off right there, goes out to a tip, and then I have another 100 feet of 1.5 inches to the next lateral, and another 100 feet of 1.5 inches to the next lateral. And you'll see that, you know, 2 out of 3 laterals are labeled as 100 feet an inch, and one of them's missing. Well, at some point, you get comfortable enough to know what you're drawing and what everything looks like, and you can start to omit a few things. During this class, I am going to do my darndest to put notes on everything and be very consistent at labeling every piece of it. There will be times where I will make mistakes because when I'm just doing hydraulics to get answers, I will crank right along and not, you know, put in a lot of information. So for the class, I will be attempting to put in lots of information. If I miss something and you're not sure, ask. Generally, the more you label and the more you accurately label, the easier it is for you to track your own work. The Y's in the hose lay are assumed. I know that I can't split hose without a Y or a T, and we all use Y's, so I make the assumption that they're there. I don't draw them in place. If you want to be an artist, that's fine. Go for it. But I try to keep it simple. We don't do friction loss for appliances anymore, so I don't even sketch them in there. They don't matter. Elevation is identified by these arrows and a number. Right here, I'm underlining it. Okay, so I have 100 feet of elevation change on this hose lay. And really that's from the pump to the highest point in that hose lay, or the highest tip, the very end of the hose lay. If it goes back down and back up again, it'll be the tip, and it'll depict between those pieces and should show you with some sort of arrow function what that elevation change really is. Nozzles. So the tip is written as a tip or a fraction. So right here it says 3/16 tip. Okay, well we know that's a tip, and we know what size it is. And over here it's just 3/8, because if it's a fraction, it's going to be a tip. So there could be some assumptions there. I will write a T instead of just a tip, just to abbreviate it when I'm writing a whole bunch of stuff. When we get into some, you know, big hose lay exercises, you'll get why you don't label every single thing. It's just a little redundant and unnecessary. So nozzles continued. In the middle here, I have one that says 20 gallons per minute. If it identifies the volume, we're talking about a barrel nozzle. And if it identifies a tip, we're talking about a fraction. So those are the two main pieces to recognize between them. Is a volume means a barrel nozzle, 100 psi. And we'll get to that part here next. But a volume means a barrel nozzle. A fraction means a tip. The hydraulics formula. Now we'll dive into the formula. So we're going to talk math, but it's pretty easy math. And we'll try and keep it easy math. There's a process that needs to be followed, so we'll try to line that out. The hydraulics formula is pump discharge pressure equals nozzle pressure plus or minus head pressure plus friction loss. It's abbreviated PDP equals NP plus or minus HP plus FL. All right. So the other way to write that formula is like this. This is what I use. I like it better. It's simpler. It's more like second grade math, which maybe that's why I do it. But mostly I think it's because it's easier to line up my numbers when I'm adding them together and I'm not using a calculator, which occasionally I'll do. So in this case, I'm still looking at NP, or desired nozzle pressure, plus or minus HP, which is head pressure, and it's positive or negative, plus friction loss equals my pump discharge pressure. All right, we're going to delve into those individual components of the hydraulics equation. So, nozzle pressure. It says determine nozzle pressure as if it's step one. It is step one. I have to put my nozzle pressure in the top of my equation. So, it's desired nozzle pressure. Nozzle pressure is 50 or 100. If I go to defining what nozzle pressure is, it's simply the pressure at the nozzle. And it is whatever it is after we've lost pressure for friction loss and for head pressure. And you end up with whatever pressure's out there. But when we're doing the calculations, we calculate it solving for nozzle pressure. So we want the nozzle pressure to be 50 for a tip or 100 for a barrel nozzle. And why do we want that? Well, a lot of the time we hear people talk about, well, it's the most efficient or the most effective. And no, that's not really it, albeit to some degree that's not an inaccurate statement. That's what it's rated at. So the Lightsaber Forester nozzle there on top is rated at 50 psi, and it's going to give you a given volume based on that 50 psi. If it's at 100 psi, it's going to give you a different volume than what we know it's rated at 50 psi, and that's fine. We can calculate that. However, do I really need to get more volume out of it, or is the volume at 50 psi more effective for me? Well, that kind of depends. Generally, at 50 psi, it's a nice smooth stream, and as I crank that pressure up, that stream starts to fall apart and fog out a little bit, which may be quite useful to my needs, but I'm also moving more volume. And if I don't know what my nozzle pressure actually is, because all I did was crank the pump up, then I don't know what I'm flowing. Your adjustable barrel nozzles, all of those barrel nozzles are going to be 100 psi. That is my desired nozzle pressure because that's what they're rated at. So what about 75 or 80 psi nozzles? They're out there, but they're not in our world in general. So 75 psi barrel nozzle is it's called a low pressure fog nozzle. That's in the structure world. We just don't use those in general. You may have some floating around, and that's fine, but generally not our issue. 80 psi is a master stream, like a monitor. And again, we very rarely have those, and we very rarely need to calculate for them. So remember that delivering the correct volume is really what we're kind of looking at. Nozzle pressure equals the volume of what we're going to get there. And that'll that helps us to figure out the rest of the hose lay. So, but that's why nozzle pressure is predetermined. That's why we say it's going to be 50 or 100, so that we know the volume we're flowing. We do pretty good at dealing with a lack of volume. We do that pretty regularly. When your nozzle doesn't have enough volume, it doesn't perform well. It feels like a lack of pressure. And we think we need more pressure when we usually need more volume. The inputs are interrelated. You need to deliver enough volume to overcome the pressure demands to flow your hose lay. But most of the time it's a volume issue when it doesn't feel like it's functioning correctly. So, nozzle pressure is 50 or 100. That's the simple answer. It's got to be one or the other. Nozzle pressure by apparatus. So, talk nozzle pressure there, just that, video demo here of the options. Forester nozzle is going to be a nozzle pressure of 50. Okay. It's not that it's its efficient flow rate or it's the safest flow rate or the most effective. It's what it's rated to. This thing is rated at 50 psi, and at 50 psi, this 3/16 tip is going to give me 7 gallons a minute. And at 50 psi, this 3 gallon a minute fog nozzle is going to give me 3 gallons a minute. So that is the point at which I know what it's doing. If my nozzle pressure happens to be more than that, I can calculate the volume that's coming out of it. But generally, we're solving for nozzle pressure so that we know what nozzle pressure, we know what volume we're going to flow because of nozzle pressure. In fact, this whole hydraulics equation piece, you can take it all out if you have a flow meter. You can say, oh, okay, well, I got 3 Forester nozzles at 7 gallons a minute. I just keep adjusting my RPM on my pump until my flow meter says 21 gallons a minute. I've hit that target pressure for 50 psi at the tip. Those are, that's kind of what we're really solving for, is that volume equation portion of it. Even though we go through all of the pressure portions to do it. And the other portion of that is that it ties back to pump performance, which we'll get to. So, Forester nozzle, it's 50 psi. That's what it's rated at. That's what it's going to give me the appropriate numbers for. Barrel nozzle. Nice adjustable KK, aluminum, 100 psi. Okay, that's what that guy is going to give you. In fact, at 50 psi, the stream out of this isn't quite as good as it is at 100 psi. Plus or minus 10 psi, you're never going to know the difference. It's just not that sensitive. But this guy's going to like more pressure, so he's going to work better at 100 psi than he will at 50. Test it. Run it and see it, just to see the difference. Maybe we'll try and do that at some point. But so these guys, when we're doing calculations, 100 psi. This guy, little cheapy plastic Lexia, barrel nozzle, again, 100 psi. This guy, big old bruiser, giant nozzle, again, 100 psi. All of these adjustable barrel nozzles are 100 psi. Okay, what else do I have? Something like that. It's gonna be 50. It's a tip. In fact, that tip's removable. All right, so we're gonna talk about water now. Water has weight. So a 1 square inch column of water, 1 foot high, weighs 0.434 pounds. Therefore, a 1 square inch column of water 2 feet tall weighs almost a pound. Okay. Therefore, a 1 square inch column of water 2 feet tall exerts a force of approximately 1 pound on that 1 square inch. So, 2 feet of water equals 1 psi. We're talking head pressure now. So that weight of water piece is just the whole gravity and elevation change. So if it takes 1 psi to lift water 2 feet, then that gives me a very simple and easy calculation. to determine head pressure. If I'm pumping uphill, I take my elevation, and in this case it's elevation gain because I'm going uphill. I divide that elevation gain by 2 and add the result in my equation. So it's a plus for head pressure. Okay, so if I go up 100 feet, I add 50 because the 100 feet, half of 100 feet is 50. All right. If I'm going downhill, I divide that elevation loss by 2 and I subtract the results because of the exact same thing, but I'm going downhill, so I'm gaining that pressure by going downhill. Head pressure, it's all elevation. It has nothing to do with anything else. Hose size, friction loss, volume, nozzle pressure, none of that affects head. Head is just elevation change. And it doesn't matter how long that elevation change is strung out over. If it takes you, 2 miles to gain 700 feet, you've still only gained 700 feet. That 2 miles piece, that's friction loss. That's a different problem. We'll deal with that later. A little clarity definition here on head pressure. The elevation gain or loss between your pump's location and the top of the nozzle set or the top of the elevation that you're pumping. If you pump over the top of a hill, you're going to gain a little bit of head pressure. You still got to get to the top of that hill. There's a little bit of a funky balance there as to how that equates, because sometimes we'll have to pump up, then down, then up, or vice versa, and the equalization of the total overall change is what we're looking at. And head pressure can eventually play some kind of funky roles, but for our purposes and what we're doing here, we're looking at the overall change in elevation between the pump and the nozzle. So for example here, it's a 100 foot of elevation drop. I divide my elevation change in half. Half of 100 is 50, and that is the pressure I gain because I'm going downhill. So friction loss, the third piece in the equation, this is everyone's favorite. It tends to confuse people, and we'll walk through it slowly. So friction loss is a function of volume. Friction loss increases as the volume increases. Okay, you might want to know that. That's probably pretty important. Friction loss is cumulative. So we calculate friction loss per 100 foot length of hose. The more lengths of hose, the more friction loss I get. Another piece you're probably going to want to know. It's cumulative, and it increases over distance. Friction loss is affected by hose size. Small hose doesn't move as much water as big hose. It certainly doesn't do it as efficiently. So the smaller the hose, the more friction loss. Friction loss has nothing to do with head pressure. It is the same whether I go uphill or downhill. And you need to use a friction loss calculator or a chart. And there's a chart in your IRPG. But use a friction loss calculator or a chart. And for this class, please use the calculator to calculate friction loss. So back to the drawing that we made, or that we referenced earlier. These are the things you need to know to be able to calculate friction loss. You need to know the hose size. You know that hose diameter. Generally, all our hoses in 100 foot lengths. So that part's easy. But you need to know the diameter and where that diameter lays within your hose lay. You need to know how long it is and how long each section of hose is between different points. And you need to make sure that's accurately portrayed in your map, your model, your diagram of the hydraulic situation. And you need to know what volume of water is flowing through each part of your hose lay. We'll break that down looking at it, and it should help. But you need to know all these factors to be able to calculate friction loss. All right, so determining the volume flowing. We're not skipping around here. You need to know the volume flowing out of each of those nozzles so that you can figure out what volume's flowing through each piece of hose in your hose lay. So we'll be looking at nozzles and how much they flow. Adjustable barrel nozzles, the nozzle is rated to flow a certain amount at 100 psi, right? So that's why we're using, for an adjustable barrel nozzle, a nozzle pressure of 100 psi. In all of our examples, that will give you a volume flow. So just like in the diagram we were looking at, it said 20 gallons a minute. Okay, well, that means it's an adjustable barrel nozzle. It's giving you the volume. Use the volume that's provided. You do not have to reference your calculator to figure out what that is. Okay, so looking here, which one's the barrel nozzle? Well, it's the one that has the volume listed. There's your barrel nozzle. So we just took a look at barrel nozzles. They're the easy one. It tells us the answer as far as volume goes. But now we're going to look at tips. To figure out the volume on a tip, you use the nozzle discharge calculator. That would be the top portion of your friction loss calculator. There are two calculators in there, nozzle discharge and friction loss. We're going to be looking at the top portion. Here we have a friction loss calculator, or that's what we call it. It's actually two calculators in one. The top portion is the nozzle discharge calculator. I'm sure you can see my cursor there or not in the video, but nozzle discharge calculator. So to start with, we'll be discussing the nozzle discharge calculator portion. And it's got the steps here, and really you're not going to use this part very often. But number one, set nozzle pressure at the arrow. So for barrel nozzles, we know that the nozzle pressure is 100 and that it gives us the volume. So you don't have to use the nozzle discharge calculator for it unless you're changing the nozzle pressure. And then it's a little more complicated. There's an extra step, and we'll address that in a completely different session. But for tips, we use the nozzle discharge calculator. And you set your arrow to 50. Arrow here in the middle goes to 50, and you leave it there. Now, down here you have nozzle bore. There's 3/16, quarter, 5/16, 3/8, and so on. That's going to show you your volume at 50 psi. So if I have 50 psi as nozzle pressure, 50 psi at the tip, a 3/16 tip is going to give me, what's that, 7.4 gallons per minute. And we round. So round to the nearest whole number. In that case, we call it a 3/16 7 gallons a minute. All right. Now, a cheat that makes it a lot easier and you don't have to pull this out and check it all the time, is just to write 7 gallons per minute or 7 next to 3/16 so that next time this comes up, you'll know it and you can just look at your calculator and it's on there. That's what I did for years and years and years, and now I just have them memorized. But I don't expect you to memorize them right away. Just know how to get them. So I would recommend writing 7 there. That way we're all on the same page and you're not using a different number accidentally in the future. So 3/16 and 7 gallons a minute. If I look at the 1/4 inch tip, I'm looking at 13. It's pretty obvious that the graduations changed there after 10. And that's 10 and a half and 11 and a half and 12 and a half and 13. And we round to the nearest whole. So 1/4 inch tip is 13 gallons a minute. I would write that to the 1/4. The 5/16 tip is 21. Again, the graduations have changed and it's going up by ones. Run the actual calculation down, it ends up it's closer to 21 than it is to 20, but just barely. So we call it 21. And a 3/8, same thing. It's 30, not 29. It looks like it's awfully close to 29, but if you run the calculation out, it's 30. So If you write 21 next to 5/16 and 30 next to 3/8, you will always have the same answers that we do because we'll be on the same page. Additionally, if you ever run into a larger tip size than that, you can calculate for them. We are not going to regularly in this course, so there's no need to go into 7/16 at 40 or the half at 52 or so on. But you could see that at 50 psi, a 1-inch tip is 210 gallons per minute, just for interest. So that is how you calculate the nozzle discharge for tips. Put the arrow at 50 and you read the tip size off the nozzle bore portion here at the bottom. And then we take our volume and we plug it into our friction loss calculators. The friction loss calculator is the bottom portion of the calculator. This is the part you actually use a lot. And the process for using this we'll just use 30 gallons a minute for a 3/8 tip as an example. Okay, so I set my arrow. You see number 1 there says set flow arrow. I set my arrow at 30. And am I perfect? Probably not. But at 30, and then I read the friction loss opposite the hose size. So this top bar is my volume flowing through that specific piece of hose. And the bottom part here is PSI loss per 100 feet single line. This is the one you're going to use, the one on the top. Note the one at the bottom says PSI loss per 100 feet 2 Siamese lines. That's parallel hose lays. We'll get to that later. For now, focus on the top portion here. Ignore this bottom portion. On the slide rule, you have 5/8, 3/4, 1 inch, 1.25 inch, 1.5 inch, 1.75 and 2 inch. And actually, if you slide her over, you have 2.5 out there. Let's see if I can get her back to 30 gallons per minute. And so if I'm flowing 30 gallons a minute through 1.5 inch hose, I have, it looks like 3 PSI friction loss. Yeah, it's 3.2, 3.1, but we round to the nearest whole number. Always round nearest whole number. The next one out here is 4, so yeah, I'm just gonna call it 3. If I was pumping water with 1-inch hose, pumping 30 gallons a minute with 1-inch hose, I'd be looking at 24 PSI friction loss. Nope, 22, because the graduations change between different pieces, and that's 20, and that's 30, which makes the mark in the middle 25, so it looks like 22. Remember, if you're only off by 1, you're probably not off very much in the overall. But try to be as close as you can. And if you're only off by 1 in 1-inch hose, it's guaranteed that you're only going to be off by 1 because you only calculate for 1 lateral. We'll get to that part later. All right, so when it gets to rounding, say we're moving 30, 25, 6, 7. 27 gallons per minute, 1.5 inch hose. What's my friction loss here? Well, it's right at 2.5. The correct answer for what we're going to use is 3. So the friction loss we get off that calculator is per length of hose, per 100-foot length of hose. So if I have 5 lengths of hose in a run, I multiply that number times 5, or whatever number of lengths of hose I have in this piece of my hose lay. And then there's rounding. Rounding is important and can kind of get a little, not complicated, but yeah, difficult. The rules for rounding: if you are less than half a PSI, you round down. If you're half a PSI or greater, you round up. So remember, in rounding, accuracy is important, but precision not as much. The whole game is a calculated estimate. So consistently round the numbers to the nearest whole number. That's the one without a decimal place. And it will work. Okay, so we're going to apply this here in a minute and actually do it, and it should make a lot more sense. But let's touch on a few more little pieces, tidbits, information about friction loss. You're going to want to know these. So some facts about friction loss. If you double the flow, friction loss increases 4 times. Okay, so double the flow, you increase friction loss by 4 times. If you half the flow, you reduce it by 4 times. 3/4 inch hose has approximately 8 times the friction loss compared to 1-inch hose. The amount doesn't really matter. The fact of the matter is, smaller hose has significantly more friction loss. You know, it's hugely significant. 1-inch hose has approximately 6 times friction loss compared to 1.5 inches. That's great. Tips for overcoming friction loss. So the number one tip is to get bigger hose. And the example is there, good friction loss of 30 gallons a minute through 100 feet an inch is 23 psi, but the same through 1.5 inches is 3 psi. That's pretty significant, and those are both hoses that we have in our possession that we use regularly. And if you went up to 30 gallons a minute through 2.5-inch hose, is effectively 0. Not that I have that around, but you gotta, plan. Bigger hose, less friction loss. You can pump water farther. Friction loss of 20 gallons a minute through 3/4 inch hose is 45, but the same through 1-inch hose is only 10. Okay, I think the point is proven that smaller hose, much more friction loss. And if you do that over a longer hose lay, it adds up rapidly. Have you ever set up a small hose lay with 1-inch trunk and 3/4 lats? And how was your fire stream? Probably not that good. It probably worked because you didn't need a lot of pressure to make things work, but your pressure was just eaten up by friction loss, and you can't push those very far. Tips to overcoming friction loss. Again, things you're going to want to remember or have access to in the future here. So one way to overcome friction loss is to reduce the nozzle pressure. If we go back to thinking about our calculator there, if I make my nozzle pressure less, it reduces the volume. So really, you're reducing friction loss by reducing the volume. If you reduce nozzle pressure, you reduce volume. That's really what we're saying there. You can reduce the tip size, maintain the same nozzle pressure. Again, I'm reducing volume, right? Because I have a smaller tip. I can do a parallel hose lay. And again, I'm reducing volume because I'm splitting my total volume into 2 hoses. So really, it's just reducing volume. There's just several ways to reduce volume. All right, so pump discharge pressure, this is what everything adds up to. It's the required amount of pressure to pump the hose lay. That's it. Assuming a nozzle pressure. So I need this for pump discharge pressure to be able to pump the hose lay, overcome all the friction loss and head pressure, and still get 50 or 100 psi nozzle pressure at the end. What does PDP tell us? It really, it's only part of the equation. I also need to know volume. I always put PDP at a volume. And the reason is because you need to use that number in some way. It's not just an answer that says turn your pressure up to 286 psi and everything will be great. It's really easy to just keep turning your throttle up to 200 and whatever works, right? So why would I need to actually go through the exercise to figure out why it takes all this? Well, if I have problems and I need to overcome those problems, then I actually have the information I can use. And the first problem is, can my pump do that? Can your engine make, 400 psi? Well, it might be able to, but can it do 400 psi and still pump you 60 gallons a minute? And the answer is, what kind of engine do you have? It kind of depends. Can your hose handle that much pressure? And there's another issue. Most of our hoses only rated to about 300 psi. So if I need 450, I'm probably not going to be able to do it. I'm going to have to change something in my hose lay to reduce the overall pressure demand. A problem. So we have problem number one in our example here. I need a better black pen. I always write my equation up. NP plus or minus HP plus FL, so nozzle pressure, head pressure, friction loss. I always write that up. If I write that up there, it gives me a good anchor point to start from. Okay, and that's going to equal PDP. Okay, it looks like my pen started working. And I start here. What's my nozzle pressure? And if I'm looking at this equation, I say quarter inch. Quarter inch means tips. And tips are, there's only two possible answers here. It's either 50 or 100. Tips are 50, right. All right, next one, head pressure. HP, head pressure. So it looks like I go up 160 feet. Half of my elevation change is my pressure. That's the key, super simple way to put it. Half the elevation. So 160 feet, half of that is 80. Half of that's 80. So I have a head pressure of plus, because I'm going up, plus 80. A little plus there, you can just erase your minus, whatever works for you. Your friction loss. The first thing to do with friction loss is I have to identify where my water's flowing. So it's about flow, volume. All right, I have quarter-inch tips. I have several. I have 4 quarter-inch tips. What does a quarter-inch tip flow for volume? At 50 psi, because that's the nozzle pressure we want for a tip, is 50 psi. What does a quarter-inch tip produce? Quarter-inch tip. How much volume out of a quarter-inch tip? So I take my calculator. I'm looking at the top arrow up here on the nozzle discharge calculator. That's the top portion of this. And I set that to 50 because it's a tip. And it's hard to do on the computer thingy. Okay, and I come down here and I'm looking at quarter-inch tips. So a quarter-inch tip appears to be 10, 11, 12, 13. Call it 13 gallons per minute. If you were like me, you wrote 13 next to your quarter and it was really easy. But I can't write it on this computer thing, so be it. 13 gallons per minute. So I'm just going to write that up here. Wow. GPM, there we go. 13 GPM. Okay, I use blue just because it makes it easier for everyone else to see, I hope. So that's what each one of those tips is flowing. Now I come out to the end of my map, end of my hose lay, and I say how much water is flowing through this piece of 1-inch hose. Well, 13 gallons a minute is flowing through that piece of 1-inch hose because that's what that tip needs to keep going. That's what that tip is leaking out. 13 to the outside. So the 1-inch hose has 13 gallons per minute. And as I follow my hose lay back, now I'm in a piece of 1.5 inches. And how much volume is in that? 13. 13 gallons a minute has to flow out here. Okay, now I come back another. I'm in this piece of 1.5 inches. Why am I not doing this? Well, because in friction loss, we only have to calculate for one. We'll get into that part in a minute. But I'm following my flow. So we can look at this and we can say there's 13
gallons per minute up here. And up here, in this piece of hose, what do I have? I have 13 and 13, so 26. All right, so 26 gallons a minute are flowing through this piece of 1.5 inch. 13 comes out here, and 13 keeps going and out the end. All right, I'm looking at this piece of 1.5 inch hose. How much volume is flowing through this piece of 1.5 inch hose? It's 39. So 39 gallons per minute flows through this piece of 1.5 inch hose. 13 comes off, and 26 keeps going. 13 comes off, and 13 keeps going. All right, last lat, also 13 gallons per minute. So as I back up, this piece of the 600-foot chunk of hose, how much volume is flowing through that? Well, I have 39 and I have 13. So 52. Is my math right on that? 39 and 13?
Yeah.
Okay. Just better make sure. All right, so I'm saying I have 52 gallons per minute flowing through this 600-foot chunk of hose up to the first lat, and then 13 comes off. 39 gallons a minute keeps flowing out, and 13 comes off, and 26 gallons per minute continues to flow down my hose lay. 13 comes out, and 13 gallons per minute continues to flow out to the end of my hose lay. Okay, that's how I track my volume. Tracking your volume is the first step in doing friction loss. So then we go to friction loss. And I like to start at the end and work my way back. The same way I tracked my volume. Start with the smaller numbers, work my way back up to the bigger numbers. All right, I write this all down on my my map, my diagram here. Okay, so I'm doing friction loss. So I come back out here to the end. I'm looking at 1 inch hose, 13 gallons per minute.
Gallons a minute, 1 inch hose. I come down here and I go 15, 14, 13. I like to count backwards. I go 10, 11, 12, 13. 13 gallons a minute. And I'm looking at 1 inch hose. I look at the top of the friction loss bar, which says PSI loss per 100 single line, and it says 4. Actually, this is a little more than 4, but I round that to 4 because we round to the nearest whole number.
So I have 1 inch hose, 13 gallons a minute is 4 PSI friction loss. So I wrote FL4. Okay, so friction loss. We're moving back down here to the next piece of hose. It's different than the first. So the next piece of hose is 1.5 inch at 13 gallons per minute.
Friction loss for 13 gallons a minute in 1.5 inch hose. Well, in this case, I'm already at 13 gallons per minute because I was just there. And where's 1.5 inch? Well, 1.5 inch is off my chart here, and that's kind of unfortunate, other than we had to talk about it sometime. And we'll cover that a little more in depth in a side conversation. But in this case, so what is the answer? The answer is it's less than 1. And we'll talk about that. Call it 1.
It's like a half. It's actually 0.6. It's just a smidge over half. And we round to the nearest whole number. So we're going to call it 1. Okay. Friction loss of 1. We'll address what happens when it's closer to 0 later. Friction loss of 1. So, move it back one more. I'm looking at 26 gallons a minute through 1.5 inch hose. 26 gallons per minute through 1.5 inch hose. Put 26 gallons per minute in my friction loss calculator and read my 1.5 inch mark, and it's
26 gallons per minute in 1.5 inch hose. So I go 25, 26, and an 1.5 hose. It looks like I am almost to 2.5, which means that since I'm below 2.5, I go to 2. So 26 gallons a minute, an 1.5 hose will be 2 psi.
It says 2. Remember, we are rounding to the nearest whole number. All right, I keep coming back. Now I have 1.5 hose with 39 gallons per minute flowing through it. So
friction loss for 39 gallons per minute, an 1.5 hose. Just this guy over here, and I'm 30. Looks like there's 40, so that'd be 35. So 39 right about there. 1.5 hose. It looks like it's between 5 and 6. I say that is less than 5.5, so I will call it 5.
And I get 5. Rounding to the nearest whole number, I get 5. All right, keep coming back. Now I have 52 gallons per minute flowing through 1.5 hose.
And then I have friction loss for 52 gallons per minute in 1.5 hose. Note the graduation changes because there I'm at 50, and it goes 50 to 60 by 2s, it looks like. 2, 6, 8, 10. So be the first. Okay, and 52 gallons per minute, I'm looking at 1.5 inches, and it looks like it is just about 9.5, but it's just under 9.5, so I'm going to call it 9. Round to the whole number. That's 9.
So I put my friction loss calculator on 52 gallons per minute, and I read my 1.5 hose mark, and I get 9. So friction loss of 9. But I got more than one chunk of hose. So it's 9 per 100. 9 per. So I have 9 per 100. There are 600 feet, which means I have 6 lengths of hose. So at 9 per length of hose, I get 9 times 6. 54. Or 54 psi of friction loss in this chunk of the hose lay. All right, to come up with this number here in my main equation, I simply add all of these together. So 54 plus 5 is 59. 61, 62, 66. Right?
Yeah.
I have 66 psi of friction loss for the whole thing. And then I add it all together, and I'm looking at 196.
Yes.
Here, switch colors. I'm not in friction loss anymore. I mean answers. Answers are green. 196. Correct? At 52 gallons per minute. It's important to put the 52 gallons per minute. It gives me a lot more information. Not required for the pre-work, but if you do it, good on you, because you're on the right track. We'll get into why we do that.
Okay, pump performance. So this is where the numbers that you calculate start to make some difference, where they start to mean something. It's not just the pressure required to pump the hose lay that I can turn my pump up to. It's can my pump work at that level? Pumps are they will perform at different given levels. So a volume pump will produce very little pressure and give you significantly more volume. A pressure pump will do the opposite. But even within that pressure pump range, you have pumps that will produce you a lot of pressure, and you have pumps that will produce a lot of volume. Some of them will do them both at the same time, like on your PTO Type 3s. Some of them will, specifically on your auxiliary pumps, a lot of your auxiliary pumps have a very noticeable performance curve, where as my demand for pressure out of the pump goes up, my ability to produce volume goes down. So I can wrap that pump up to its max RPM, and if I need pressure in my hose lay, I won't be able to move as much volume. If I need volume in my hose lay, I won't be able to build as much pressure. If I need both volume and pressure, I may have to find a bigger pump or a different way to do it. So this is where pump performance comes into play. So this is a pump performance chart, and for the in-class portion and even the virtual classroom portion, you will get several other pump performance charts that you can use for reference, both for the class and in the future. This one has a whole pile of small pumps in there, and then a couple of high pressure pumps. So we'll focus on the Mark III at the top just because everybody's familiar with it, and that'll work for us. If I'm looking at the top there, it gives me a pump pressure. Free flow is basically building 0 PSI. It's just free flowing out of the pump head, which would theoretically be maximum volume. Even though it's not always the case, it's pretty darn close to it. And then I have 50, 100, 150, 200, 250, and so on. And so we had free flow shutoff pressure. It means you're moving 0 gallons per minute. It's just the pump, cranked up to its maximum, and the discharge is shut off to build the maximum amount of pressure. So when you look at that Mark III out there at the end in the 400 column, it says 0 at 380 PSI. That's saying that 380 PSI is the shutoff pressure. And that just gives me two ends of that performance curve. And then I have all these little pieces of data in between. And these performance curves can vary a bit. They're based at sea level. They assume everything is operating perfectly. And even at that, you'll find a discrepancy in them at times of a few gallons per minute from one person's performance chart to the next. Some of these are very old, but still useful. So they have a tendency to get recycled. And I don't know anybody who's really sat down and built a new one or test built a new one. So we're operating off some information that may not be perfect, but it's information that gives us some reference. And so I'm just going to focus on the Mark III there. It says that at 50 PSI, a Mark III will give you 89 gallons a minute. At 100 PSI, it can no longer do 89 gallons a minute. It'll only give you 78 gallons a minute. At 150 PSI, you're looking at 65, and so on. You get up there in that 350 PSI range. If you need 350 PSI out of your Mark III, you're only going to get about 9 gallons a minute out of it, which isn't very much. So you start to see some of the limitations. If I look at my hose lay and I need, say, 60 gallons a minute in this hose lay, I can look at this chart and say, okay, well, Mark III can give me 60 gallons a minute and do 150, maybe 160 PSI, something along those lines. And that's where the chart starts to become handy. So let's reference problem 1 that we just did. And it said that we were 196 PSI for pump discharge pressure at 52 gallons per minute. So you can look at either the pressure piece or the volume piece. Either way, 196 is awfully close to 200, and that's right at 52 gallons a minute, which is what I need. So according to this chart, the Mark III will pump that hose lay, but it's pretty much at its maximum, which is fine. That's where Mark III likes to run. But remember, when you're setting up a Mark III and you are doing, recirculation and all of that stuff, you're not going to be able to be recirculating a lot of water. You're going to need most of the performance of that pump going straight into your hose lay to be able to pump that hose lay. Also, at high elevation, that pump may not be able to do that. Its performance is going to be impacted by elevation, and you might be too close to be able to pull that off. So you're right in there, though. I would certainly give it a go. So I mentioned there's a lot of different performance charts out there. I will provide several for you to use and reference well into the future, I hope. Also, they're available in a lot of different places, and they come in different formats. The chart we just looked at is pretty common in general, but if you take that chart and you graph it in a spreadsheet, you can just put that in a spreadsheet and build a graph out of it, or graph paper, or whatever. I'm sure there are other applications that do a better job of it these days. You can graph that performance curve. In this case, it's kind of a straight line down. Generally, they kind of go down, up. They go up a little bit before they start to taper off down, but you get the general idea here. So if you graph it like this, it can make it a little easier to interpret. So it gives me 210 gallons a minute at 50. I'm all off. At 210 PSI, I'm looking at 50 gallons a minute. That sounds a lot better. And so I want to know 200, then I can actually kind of follow that line down to the 200 mark and say, okay, well, it's not 55. It's probably more like 52, which is exactly what the other one said, which is funny because I didn't think about that. But anyway, it's just another way to extrapolate data, and I wouldn't consider them so accurate that you could be that precise with it. Heck, we're not that precise with our calculations of the needed pressures. But boy, it's a tool that helps you to troubleshoot when you're having issues. That's for certain. And then you also have a Mark III pump page on your RPG. The RPG has lots of data in it. Everybody's looked through it, and it's kind of hard to find. It's probably not even on page 93 anymore. Note the color of the cover is different than what it is today. But there is pump performance data in there, and that's cool. It still should be in there, and we should have that for reference in a pinch. I carry the charts with me because I pretend to be a water handling specialist, so it gives me a little bit better data. My charts also cover more than just a Mark III. If I'm looking mostly at Mark III data and time, then yeah, this works just fine. This is good information. So workout problem 2. Note that your head pressure is probably the new complexity in the game. Work on that. We'll take a pause, and we'll fill in the how-to on problem 2 here momentarily.
And recording. All right, so here we have problem number 2. Problem number 2, we have a pump. Pump pumps up 190 feet, down 70 feet, and then over to our actual hose lay where we're fighting fire. There are 4 3/16 tips in this problem, in this hose lay. So the first thing I do is I write up my equation up here so I have something to work off of. That's always my first step. And I go to my equation, and number 1 is nozzle pressure. So I look at the nozzles. Nozzle pressure is always one of 2 answers, 50 or 100. And if I have 3/16 tips, forgot my inches mark, 3/16 tips, it's going to be either 50 or 100, and it'd be 50. Tips are always 50. So nozzle pressure is 50. And recording. All right, head pressure. So in this case, I go up 190 feet, but then I come down 70 feet, okay? So my total head pressure needs to pump this hose lay, I'm gaining this 70 over here, I'm losing that 190. I can subtract my 70 off my 190, I get 120. 120 feet of total elevation change in this theoretical closed system. So I'm looking at 120 feet. If I'm looking at 120 feet, that's half my elevation for my head pressure. So I have 60 PSI for head pressure. And it is a plus. I am still going uphill more than I am going downhill. All right, now we are looking at friction loss. All right, so here's our friction loss. You'll notice I grabbed the blue pen because the first step in friction loss is volume. If I take my 3/16 tip and I put it in my nozzle discharge calculator.
So we have 3/16 tips and 3/16. So a tip is going to run, we're looking at the top part of our nozzle discharge calculator here, the top part of our calculator, which is the nozzle discharge calculator. And I plug in my nozzle pressure, which for a tip is 50. And I look down here at my 3/16 and it looks like it's 7. Oh, and it's in between 7 and 8. 7.2, 7.4-ish. Round to the whole number, we call it 7.
Over 7. But we round to the whole number, generally. So we're going to go 7 GPM. All right? And they're all 7 GPM. So every nozzle is moving 7 gallons per minute. Now I start tracing my water back. All right, so I look at my last lat. So I'm out here at the end. I have 1-inch hose, and how much water do I have flowing through that? I have 7 gallons per minute. Okay, and then in this next piece, which is 1.5-inch hose, I also have 7 gallons per minute. That 7 gallons per minute flows through this hose and out that lat. Next piece, 1.5-inch hose, I have 2 lats that it's feeding. So that'd be 14 gallons per minute. All right, and 14 gallons per minute flows through this hose, 7 comes out, 7 keeps going out to the end. All right, so I back it up one more time. And the next piece of 1.5-inch hose has 21 gallons per minute. Okay, and the next piece of 1.5-inch hose, which is the 2,000 foot mark here, has 1 more lat that it's feeding. So I'm looking at 28 gallons per minute. So we'll just do a quick follow on where the water's flowing. I have 28 gallons per minute flowing out of my pump, up and over to this mountaintop, and down, and then out here, and then 7 gallons per minute comes off, and 21 gallons per minute keeps flowing. 7 gallons a minute comes off, and 14 gallons a minute keeps flowing. 7 gallons a minute comes off, and another 7 gallon a minute keeps flowing, and out to the last nozzle. That's what my water's doing. And from there, I can calculate friction loss. All right, well, I didn't write 7 gallons a minute on all these lats like I did on the first one. Yeah, I wrote it up here, and it's somewhat implied. And I only do friction loss for 1 lat. So I only have to calculate it for 1. Why? Well, the easy answer is it's a rule. That's the easiest answer, and if you need an easy answer, there you go. It's a rule. You only do it for 1 lat, the biggest one. Whatever the biggest friction loss is going to be. If you had different sizes, it'd be the biggest one. Okay, the complicated answer is that we think of a hose lay as a pressurized vessel, and pressure is equal in all directions, even though in reality, anyway, pressure is equal in all directions. And so if I overcome enough friction loss to deal with this lateral, I will have overcome the friction loss needs for the rest of the laterals. They are effectively in parallel. That's the complicated answer. Easy answer, it's a rule, 1 lap. Let's talk friction loss. All right, friction loss in this one, I'm gonna document it just slightly different, give you a different approach. This is really handy for a lot of people. And I'm gonna go friction loss of 1, and then ultimately I'll do more than just 1. But I don't know how many yet, so we'll get there. Loss. I wrote the friction loss 1, friction loss 2. We'll add to that as we go. It's just a different way to keep track of this. It's gonna be really helpful for some people. But I still write it out here. And one reason I still write it out here is because at some point when I'm trying to troubleshoot my system, if I know where certain things lay on my map or my diagram, it'll help me out. So let's do friction loss. I come out here to my end, because I always start out here at the end, and I have a piece of 1-inch hose, one piece of 1-inch hose with 7 gallons a minute in there.
So that being said, we're looking at 7 gallons per minute in 1-inch hose. So 7 gallons per minute's way down here. I'm looking at the bottom part of my calculator now, the friction loss calculator, because we are doing friction loss. There is 7 gallons per minute. In 1-inch hose, I am between 1 and 1.5, and I am closer to 1, so don't do 1.5 anyway. It's less than 1.5, so we round to the whole number, it will be 1. Friction loss of 1.
So my friction loss is 1. So my friction loss is 1. All right? And then I come back, and now I'm looking at 1.5-inch hose, 7 gallons a minute. I don't even have to move my friction loss calculator. It's already on 7 gallons a minute, right?
And then I have 7 gallons per minute in 1.5-inch hose. And that's not even on my chart. It's way out there. It's less than 1.
1.5-inch hose. Well, shoot, where is it? It's low on my friction loss calculator. It's less than 1, right? This is one of those things. It's like, well, how much difference does it make if I put a 1 in here or if I put a 0? Both of those answers can be correct. The real answer is that I have less than 1 psi of friction loss. There is less than 1 psi of friction loss in this piece of hose. You can totally say I have 0 because plus or minus 1 psi isn't going to make a difference, and we already know that it's going to be less than 1. It'll be like plus or minus 0.5 psi. So it could be 1 or it could be 0. It doesn't matter. A lot of people like to err on the side of caution and make sure they have enough pressure, and they like to put 1 in there. We call the friction loss 1 on this piece. And I put FL of 1 up here. You know, the reality is it's very insignificant friction loss in an 1.5-inch hose moving that low of volume. And over a 100-foot chunk, it's insignificant in the overall equation. If it's less than 1 psi of friction loss over, say, 2,000 feet, me saying 0 is probably not accurate because there is some friction loss in there, and it's going to add up, and I'm going to have to overcome it. But me saying 1 probably isn't accurate either because I'm overestimating my friction loss needs over this huge, long chunk of hose lay. So just be aware of that. When you get into these really long hose lays and you come up to the point where you're looking at 0-ish or 1-ish of friction loss, that's where you may actually start splitting it. But generally, we're going to go to the whole number. Go to the whole number, keep it simple. In this case, we're going to use 1, it rounds to 1. All right, so I look at my next piece of hose. I just bring her on back because I don't have to deal with these lats. 14 gallons a minute through 1.5-inch hose.
And then I'm looking at 14 gallons per minute in 1.5-inch hose. That over will go 14 gallons per minute in 1.5 inch. That one is also less than 1, but it's pretty close to 1.
Pretty close to 1. Up here. here, I'll make myself another little spot for friction loss, and it's another 1. All right, I bring her back another notch. Now I'm looking at 21 gallons a minute through 1.5 hose.
21 gallons per minute, 1.5 hose. 21 is and 1.5 hose. Oh, it is right, just a smidge above the 1.5. We're gonna call that 2. Notice how the last two kind of offset each other in the averaging and ended up with basically pretty close to the same number anyway. That's why it works.
It should tell me about 2. All right, and I come back again, and I'm looking through at 28 gallons per minute through 1.5 hose.
At 28 gallons per minute, 1.5, so 25, 6, 7, 8 gallons a minute, 1.5 hose. Looks like 3, and that would be 3 per 100.
I put 28 gallons per minute in my friction loss calculator, and I read the 1.5 hose, and I should get 3. I'm looking at friction loss of 3 per 100 because that's a long chunk, like 2,000 feet long. All right, and then I go 3 times the number of lengths of hose I have in it. So 2,000 feet takes 20 lengths of hose, so that's 3 times 20. My friction loss is 60. All right, come up here, FL5 is going to be 60. I now have some answers. Now I have some stuff to work with. So let's see, I got, if I add all of this together, I get 50 plus 60 is 110. 11, 12, 13, 14, 15, so 175. Green pen. At 28 gallons per minute. And that's the answer.
So with problem 2, I am looking at 175 PSI at 28 gallons per minute. And if I go back and reference my pump performance charts, can a Mark III, we'll just stick with the Mark III for simplicity at the moment, pump 175 gallons per minute, can a Mark III pump 175 PSI at 28 gallons per minute? And if you reference that chart should tell you that yes, it can. So generally, this is where I'm taking a break to not lose my place and make sure we go through a bunch of hands-on exercises. In this case, we've concluded our basic refresher for wildland hydraulics, and hopefully this gives you the information you need to be able to successfully complete the hydraulics problems in the pretest. And we will continue on with learning about hydraulic stuff as we go forward. This was just the introduction, just the scratch on the surface. If you have questions or are running into issues, feel free to reach out to us through the training center.